Thinking about quantum gravity. Welcome back. Chapter 1D, the problem of time in quantum theory. Let us recall that in the previous lecture, we had introduced these two levels of dynamics. Level 3 is classical dynamics. Level 2 is quantum theory on a classical spacetime. At level 3, matter fields are treated according to the laws of classical mechanics. It could be Newtonian mechanics, it could be special relativity, or it could be the general theory of relativity. Spacetime is classical. It's denoted by CST, which stands for classical spacetime. It could be the absolute time and the space of Newtonian mechanics. It could be the spacetime of special relativity, or it could be the curved spacetime of general relativity. The point to note is that in classical dynamics, matter fields, bodies, electromagnetic fields, etc., as well as spacetime, they are both classical. At level 2, matter fields or particles, say electrons, protons, neutrons, these are treated by the laws of quantum theory, which we have already talked about. But spacetime continues to be classical spacetime. So note the difference between level 2 and level 3. The nature of matter changes from classical to quantum, whereas spacetime continues to be classical. Let us for a moment ask this question. Why is it not that at level 2 both matter as well as spacetime are quantum? So we'll see in a moment that that is actually a more natural situation where matter and spacetime are both quantum, and in fact level 2 is an approximation which actually breaks down under certain situations, and that is very central to today's discussion. So we come back to level 2. We spend a lot of time understanding it. Here matter is quantum, spacetime is classical. I say that level 2 is fundamentally problematic. It is incomplete. Of course, quantum theory lives on a classical spacetime. It works extremely well, but there's a deep issue there, which is what I want to talk about today. And that's what I mean by the problem of time in quantum theory. Let's have a look at the Schrödinger equation. We could do this argument with quantum field theory also, relativistic quantum field theory. Doesn't matter, it's just that the Schrödinger equation is easier to describe. Look at the time part on the left side of the Schrödinger equation. It is part of a classical space-time. What does that mean? It's part of a space-time which is produced by classical bodies according to the laws of general relativity, or even you could think of Newtonian gravitation, doesn't matter. What is important? That this time t, this coordinate time on the space-time manifold, it has nothing to do with the quantum mechanics as such. It is part of a classical space-time geometry whose laws are those of general relativity. This geometry is produced by classical objects like the Earth, stars, galaxies. A classical universe has a classical time. But now there's a problem. These classical bodies are by themselves a limiting case of the Schrödinger equation, obviously, right? Classical objects in some approximation emerge from quantum theory. So look at the cyclicity, the circularity in this construction. Time is classical. Classical spacetime is produced by classical bodies, but these are a limiting case of quantum theory. So it seems as if quantum theory depends on classical time, but classical time comes from quantum theory because classical time is produced by classical bodies, which are a limiting case of quantum objects. So we have a problem. There's a circularity in the argument. Quantum theory, again in a stark way, depends on its own classical limit, and we know that can be problematic. At least at a fundamental level, things should not be like that. Why should a theory have to appeal to its own classical limit for its description? So let's see a little more carefully why that can be a problem. Imagine for a moment that there are no classical bodies in the universe. You could make a picture like this. There are stars and galaxies and planets. These are all classical. They are producing a classical space-time geometry. Imagine that in the intergalactic space between galaxies, there are free electrons, free protons, free neutrons. We can imagine such a scenario, and all of them are described by the laws of quantum mechanics simply because they are microscopic objects. So this is quantum theory in a classical space-time. The classical space-time is produced by these classical bodies, and in the intergalactic space there are these quantum particles, electrons, neutrons, protons, etc. For a moment, let's think that the classical objects are not there. Just get rid of planets, stars, galaxies, all these heavenly bodies which produce the classical universe. Just by, let's say, a magic wand, get rid of them, and you only have these quantum objects in the universe. So we might think there still is a background space-time, no objects, so the background space-time is classical, and on this classical space-time there are these quantum particles. What's the problem with that? The problem is the following. Let's ask this question. Having removed all these classical objects from the universe, can there still be a classical space-time geometry? Two parts to this question. Can there be a metric? Can there be a space-time metric, the G mu nu, which behaves classically? We'll see the answer is no. Underlying that metric, underlying the metric described by general relativity, can there be a classical space-time manifold? Again, you'll see that the answer is no. This seems a bit counterintuitive, but it is true, as we'll argue. So, if you do not have any classical bodies in the universe, you cannot have a classical metric, you cannot have a classical space-time manifold. So, if there are only quantum matter fields in the entire universe, the gravitational field they produce would also possess quantum fluctuations. So, it's easy to make a picture of this. We have all these quantum objects that I said are left when you have switched off the classical bodies from the universe. These quantum objects are going to produce their own gravitational field, however small. It will have fluctuations. Anything quantum produces a field that has fluctuations. Unless you assume by hand that the semi-classical, the so-called semi-classical theory of gravity holds. What does that mean? Suppose you have a quantum source. Quantum fields calculate their energy momentum tensor. It's an operator. Take its expectation value in some state. Call that the source. And that source acts on the background spacetime so as to produce a classical gravity. So that's what we call semi-classical gravity. Classical gravity sourced by quantum fields in some expectation value of some state. So if we say that quantum fields produce classical gravity, that's the theory of semi-classical gravity, and one can argue that in many ways it's actually quite implausible. Some people like to believe the gravitational field is necessarily always classical. There's nothing quantum about it, but I think that's really implausible. You cannot, under all circumstances, have quantum fields producing classical gravity. It can happen that under some very special conditions, some very special states, say in coherent states, which are very classical in nature. In such states, quantum matter could produce classical gravity, but not in general. Okay, so what are we saying? If you have only quantum objects in the universe, their gravitational field will have quantum fluctuations. So you cannot have a classical metric. Okay, if you get rid of the classical bodies from the universe, only quantum objects, you cannot have a classical metric. Can you have a classical space-time manifold underlying it? The answer to that is also no. We'll come back to that in a moment. That's a little more subtle. The metric part is easy to see. Quantum objects, quantum fluctuations in the gravitational field, no classical metric. Now, what happens? These quantum fluctuations destroy the underlying space-time manifold as well, rendering it physically meaningless. So let's form a picture. We have these quantum objects. We are saying they will produce a fluctuating metric. Now, there is something known as the Einstein Hole Argument, which we'll talk about in detail in a moment. There's a consequence of the Einstein Hole Argument that a classical metric field must overlie the spacetime manifold in order to allow a physical interpretation of the point structure of the manifold. That's quite a mouthful. Let's go over it again. The Einstein Hole Argument says that if you want to give a physical interpretation to the space-time points on the space-time manifold, they must lie on top of the space-time manifold a classical metric. This is the Einstein Hole Argument. We'll prove it shortly. Now, if you need a classical metric field to give a physical meaning to a space-time manifold, and if you have only quantum objects, those objects cannot produce a classical metric field as we just saw because of quantum gravitational fluctuations. It then follows you cannot have a physically meaningful, a measurable space-time manifold in the presence of a quantum fluctuating metric. So now comes the real problem. How does one describe quantum dynamics of quantum objects if the universe is not dominated by macroscopic objects and does not possess a classical space-time manifold? So how did we land up here? We got rid of all the galaxies and stars and planets with that magic wand. Imagine for a moment that they are not there, left with only quantum particles in what was earlier the intergalactic space. These objects, these fellows cannot produce a classical metric, and it only has a quantum fluctuating metric. Because the metric is not classical, it is undergoing fluctuations. Then according to the Einstein Hole Argument, you cannot meaningfully, you cannot no longer operationally define a underlying space-time manifold. So how do you do quantum mechanics then? In a universe in which there are no classical objects, such a universe in principle is of course possible. You can imagine it. Only quantum particles, only microscopic particles in the universe. No classical metric, no underlying space-time manifold. How do I do quantum mechanics? So go back to the Schrodinger equation. The t in that Schrodinger equation was a classical time. Now I no longer have that classical time because I no longer have classical objects in the universe in this particular setup. How do I write down the Schrodinger equation? Del psi by del t. What is t? T is no longer there. So notice, in this subtle manner, quantum theory depends on the presence of classical background objects in the universe which dominate the universe. Only then you can have a classical space-time geometry. Without a domination by macroscopic objects, no classical metric, no classical space-time manifold, but I must be able to do quantum mechanics. There are these quantum particles. So how do we do quantum mechanics without space-time manifold? That's the central question. And as I said, as a matter of principle, one ought to be able to describe the quantum dynamics of free particles under such situations. Namely, if there's no space-time manifold, you still have to be able to do quantum mechanics. That brings us to the central conclusion of today's talk, central to almost the entire discussion in this lecture series. It therefore follows that there must exist a reformulation of quantum theory which does not depend on classical time. If you want to describe situations where there are no classical objects in the universe, you need to be able to reformulate quantum theory without using the classical time t as we saw in the previous slide. So you have to be able to rewrite the Schrodinger equation without using classical time, and that's very, very important. If we do not work with such a reformulation, we will show in the next few lectures, we run into the troubles of quantum theory. The problem of quantum non-locality, the problem of absence of macroscopic superposition, the quantum measurement problem, they all result from the fact that we are using a formulation of quantum theory which depends on classical time. This looks like a very radical statement, so we'll elaborate it in the coming lecture. So what I'm saying is, if we write down on the reformulation of quantum theory without classical time, and if we understand how to come from that reformulation to the standard one in which classical time is there, we actually find a solution to the measurement problem and the non-locality puzzle if we can go from a situation where there is no classical time in quantum theory to a situation where there is classical time in quantum theory. And finding, this is quite obvious now, finding such a reformulation which doesn't depend on classical time, this paves the way towards a quantum theory of gravity. That's inevitable, that's obvious, isn't it? You are now going to ask for a way of describing quantum theory which does not use classical time. The moment you don't have classical time, you have something other than classical time, call it maybe quantum time. You already are into the realm of quantum gravity. So what led us to quantum gravity is realizing that quantum theory on a classical spacetime can only be an approximate description. We need a better description which has a quantum time, and lo and behold, that is already a glimpse of quantum gravity. Okay, so now let's come to this Einstein Hole argument. What does the Einstein Hole argument say? Let's recall, it says that if you want to be able to, in a physically meaningful way, define a classical spacetime manifold and measure its points operationally, you have to have a classical metric field lying atop the spacetime manifold. Cannot separate the manifold from the metric which is on top of it. If the metric is undergoing quantum fluctuations, you can no longer talk of or define or hold on to underlying spacetime manifold. This is a consequence of the Einstein Hole argument. So let's see what the argument is, where the hole comes from. Let us imagine there's a situation. You have this manifold M, it has matter fields everywhere except in a hole H inside the manifold. So the manifold doesn't have a hole, but there's a region in the manifold which is empty of matter. So it's empty, so that's why I'm calling it a hole. So there's matter everywhere around outside H, but inside this region H, there is no matter. Now, the only field present in the hole H is the gravitational field described by the metric G mu nu. It's obvious, gravity is there, no? So it's like you have a hollow ball and a sphere, let's say a hollow sphere. So that's your hole. Inside the sphere, there's no matter. Outside the sphere, there is all sorts of matter. So obviously, the matter outside will produce a gravitational field inside in general. That is denoted by this symbol G mu nu. Now, a bit of technical language, but easy to explain. Consider an active diffeomorphism phi on M, which is by definition identity outside the hole and on its boundary, but different from identity inside the hole. So what does it mean? An active diffeomorphism is nothing but a coordinate transformation which maps points to other points. So I suppose I make a transformation from x to x prime, where x prime is some function of x. So the point x gets mapped to the point x prime, which is defined in terms of x by this relation x prime equals f of x. This, when we say an active diffeomorphism, it's a coordinate transformation which we actually think of as moving the point x to the point x prime. So here the diffeomorphism operator is denoted by phi. Phi will act on some point in the manifold and move it to some other point, say x prime. So I choose a particular definition of this diffeomorphism which is such that we don't move the points, don't make any coordinate transformation outside the hole. Phi is unity, it's identity outside the hole. So outside the points don't move, but on the boundary also the diffeomorphism is identity, but it is different from identity inside the hole. That is, we are now going to make a coordinate transformation only inside the hole. Okay, so clearly the stress tensor T mu nu remains unchanged under this diffeomorphism all over the space-time. What does it mean? Outside, the coordinate transformation is such that the coordinates have not changed. There's T mu nu only outside. Inside, the coordinates have changed, but there's no matter inside. So T mu nu inside is 0. So you say under this particular coordinate transformation that we are making, there's no change in T mu nu. The value of T mu nu at every point remains unchanged. However, inside the hole, the metric changes under the diffeomorphism. Say from G mu nu at P at the point P to phi star G mu nu Q at the point Q, where Q is the point to which the point P is mapped by this active diffeomorphism. So what does this mean? The metric inside the hole is going to change even though T mu nu doesn't change because it's always 0. The metric at the point G mu nu of P is mapped to the metric G mu nu at Q with phi star acting on it. So what does that mean? Point P has been mapped to point Q. The coordinate transformation is going to change the metric. In which way will it change? There will be some G mu nu. The diffeomorphism acts on G mu nu. It takes it to a different G mu nu, which is the G mu nu at the point Q. So it is in this sense that the metric is changing. The diffeomorphism acting on the metric, it implies a change both in the point is also moved, and it implies a change also in the metric itself. Now, since T mu nu has not changed, it is natural to expect that the physical gravitational field has not changed either. So you have changed the metric. You change the metric from G mu nu at P to phi star G mu nu at Q. But since you have not changed the stress energy tensor distribution at all, on physical grounds you expect that the gravitational field doesn't change. Matter produces gravity according to the laws of general relativity. No change in the matter distribution. The gravitational field should be the same even if the metric has changed. Okay, now it gets interesting. How to describe that there's no change in the gravitational field? Einstein appeals to general covariance. What does that mean? The metrics G mu nu at P and phi star G mu nu at Q both describe the same gravitational field, right? The metric was mapped from G mu nu P to phi star G mu nu at Q, and both these obviously must describe the same gravitational field. That's the, you say gravitational fields do not change under coordinate transformation. Their physical content does not change. The curvature scalars will not change. That's what it means. But Einstein realized that this general covariance comes at a heavy price. What does that mean? We are saying that the fields G mu nu at P and phi star G mu nu at Q are both to be regarded as physically identical, but that is possible only if the points P and Q are also regarded as physically identical. You see what's going on? G mu nu mapped to phi star G mu nu, those you want to think of as physically identical, but the only way you can do that is you have to identify P and Q. These were supposed to be distinguishable and separate points in the space-time manifold, but no, general covariance. If you want to retain general covariance, you are losing the identity of the points P and Q. They are no longer physically separate, they are physically identical. Thus, it is a consequence of general covariance that points on a space-time manifold cease to have any physical meaning as separate, distinct points of a space-time. This is very important, often not emphasized. And this is the essence now of the Einstein Hole argument. We are coming to it. That general covariance takes away from you the physicality of the underlying space-time manifold. Of course, you want that physicality back. You want points P and Q to be different. That's not possible though if you have general covariance. The only way out to restore a physical attribute to points of the space-time manifold, that is to consider them as separate events, is through the presence on the manifold of a specific dynamically determined metric tensor field. Why? What does that mean? See, we came to the conclusion that points lose their separate identity because of general covariance. There's a way out. What can you do? You put a marker on these points. You say that there's a metric at P which is determined dynamically by Einstein equations. There's a metric at Q. So the way to distinguish points P and Q is to have something sitting atop it. If there's nothing on top of the space-time manifold, then you lose their physicality, their separate identity. So you put a marker. It's like, putting a flag at point P, a different flag at point Q, and then, you have a signature. You can say, oh yes, this is P, this is Q. You need just some classical dynamically determined field. Any marker would do. Electromagnetic field would do, for example, but it's not universal. The only universal field available to us is the gravitational field. I mean, it's produced by all objects. Electromagnetic fields are produced only by charged bodies. But the metric is always available to us. So what is the conclusion? That in order to give a physical meaning to the underlying points of a space-time manifold, you need a metric on top of it. This is the Einstein Hole Argument. Yeah? General covariance implies that to maintain physically meaningful picture for the underlying space-time manifold, you need a metric on top of it. That's the Einstein Hole Argument. The metric tensor field serves to provide a label to the points. This is what I call flags. Okay, so we're almost done. So come back to the situation where there were no classical objects in the universe. There were only these quantum objects. The metric is now undergoing quantum fluctuations. One no longer has a classical metric sitting on the space-time manifold, because remember, classical metric is produced by classical bodies. If there are quantum fluctuations, because there are no classical bodies around, only quantum fluctuations, you do not have anymore a classical metric sitting on top of the space-time manifold. You have a metric undergoing quantum fluctuations. So the flag is lost, you see. If the flag itself is stochastic, if the marker itself is undergoing fluctuations, how will you use it to separate point P from Q? How will you say this is P, this is Q? You can't say that, because the flag is not classical. The flag is undergoing quantum fluctuations. It has some one value at one time, then a randomly different value at the next instant. So the identity is lost, you see. Okay. This is also emphasized by Steve Carlip in his nice review of many years ago on quantum gravity. So he says, for us, the significance, he refers to the Einstein Hole Argument. You can go and have a look at that paper. For us, the significance of the Einstein Hole Argument is that we cannot view the metric as merely a superstructure sitting atop a physically meaning set of points that make up a space-time. The manifold and the geometry are fundamentally inseparable, and quantizing the geometry really does mean quantizing the space-time itself. In other words, he's saying, if the geometry is undergoing quantum fluctuations, if the metric is undergoing quantum fluctuations, then the underlying space-time manifold also has to be quantized. Namely, it cannot be classical. See, for Carlip, this is an argument for quantum gravity. Namely, if the metric is undergoing quantum fluctuations, you lose the space-time to quantize everything. We are looking at it in a different way. If the metric is undergoing quantum fluctuations because there are no classical objects around, then you lose the space-time manifold. You cannot describe quantum mechanics by a Schrödinger equation in the absence of classical bodies, and that is why you need an equivalent reformulation of quantum theory which does not refer to classical time or to classical spaces. Space part is not important because the wave function. The states live in Hilbert space, but even then, even if the states live in Hilbert space, they are evolving with respect to classical time. And if you don't have classical time because you don't have classical bodies, in those situations, you have to be able to reformulate quantum theory without a classical time. And that is the central conclusion of today's talk. So come back to the two levels of dynamics. Level 3, you already know, we talked about classical dynamics. Level 2 is what we discussed today, that it is problematic in the sense that level 2 is approximate. There ought to exist an underlying level which we will call level 1. At level 1, time will no longer be classical. So you see, we are moving away from standard quantum theory, already talking of time which is not classical. And how were we led to it? Because we saw that level 2 is only approximate. Level 2 requires the existence of classical macroscopic bodies. When those bodies are not there, you go down from level 2 to level 1, in which time is not classical. In fact, space is also not classical. Now, ponder for a moment. If you are at level 1, where time is not classical, you will have to find a way to come to level 2. Namely, you bring those classical bodies, those planets, stars, and galaxies all back into the universe. When that happens, your spacetime is level 2, QT and CST. So, in the presence of macroscopic classical objects, we must be able to go from level 1 to level 2. Now, that's highly non-trivial. You're asking, how does classical spacetime arise from a non-classical spacetime when you go from no classical bodies around to classical bodies around? If you think over it for some time, you will be able to conclude, you'll be able to visualize that if I can explain how non-classical spacetime becomes classical, that mechanism has everything to do with solving the measurement problem with absence of macroscopic superposition and even the quantum non-locality puzzle. Remember, non-locality is a puzzle at level 2, but now we are saying there is, for reasons just described, there is an underlying level which is level 1 in which time is not classical, and already that should give you a hint that there is no non-locality puzzle really at level 1 because there is no classical time. Non-locality is a problem of using classical time. So we will see that spontaneous localization, which we'll talk about in the coming lectures, spontaneous localization is a very natural mechanism to go from level 1 where time is not classical to level 2 where time is classical. And when you invoke spontaneous localization to go from non-classical to classical time, you actually also solve the measurement problem and the non-locality puzzle. So once again, you see this beautiful connection between quantum foundations and quantum gravity. On the one hand, you have the measurement problem, you have the non-locality puzzle. These are issues in quantum foundations. And then we introduced a new issue. Not so often it's talked about, but if people agree the problem is there. The new issue that we talked of in quantum foundations today was the so-called problem of time. There ought to exist a reformulation of quantum theory which does not have classical time. And the moment you have such a reformulation, you already are in the realm of quantum gravity. So that was all for today. Thank you for listening, and I'll see you next time.